Hi, so in this video we're going to be doing some worked examples. So this is going to relate to the concept video that we just did for thermal physics. Okay, so this is just the introduction to thermal physics, which we just did a little while back. And yeah, so we can look at some worked examples for that before we move on to phase changes. Okay. So now let's look at the first worked example over here. So as we can see over here, a quantity of heat, right? So a quantity of heat equal to 9800 joules is being absorbed by a piece of iron of mass 1.8 kilograms, and the specific heat capacity is given by this formula, by this value. Okay. So yeah, before that, I'll just say that this comes from the K. Sawkers textbook, so you can use that as reference material when you're looking at the videos. Okay, and also these videos belong to Deep Think Mathematics. Okay. All right. So that is for the copyright purposes. So now we can, now that that's out of the way, we can move on. Okay, so in this case, you're given the value of the heat, which is Q. You're given the mass M, and you're given the specific heat capacity C. So they're saying calculate the temperature increase in the iron. So for part A, it's simple. The way you can say it is that you know that the heat is equal to mass times specific heat capacity times change in temperature, which is MC times the final value of the temperature minus the initial value of the temperature. Now the mass they've already given, the heat they've given to you is 9800 joules. The mass is 1.8 kilograms. The specific heat capacity for iron is given over here. It's 450 joules kilogram per Kelvin, which they also give over here. So you can just put that in. So this is 450 joules, 450 joules per kilogram per Kelvin. And so now we don't know the change in temperature, so that's what they're asking us to find. Okay, so all we do is that we just solve for delta T. It's a simple equation. So delta T in this case is 9800 divided by 1.8 times 450, and that gives us the answer for 12.1 Kelvin. Okay, so that's part A. So now we can look at part B, which is that in this case, if you see the heat of 9800 joules was removed from 3.2 kilograms of water, initially at 4.48 degrees Celsius. The specific heat capacity of water is given over here, so calculate the final temperature of the water. So for part B, so I'll erase part A, and if you want to copy this, you can rewind it. Okay, you can rewind the video for that. For part B over here, once again we simply use the formula that Q is MC delta T, and this is just mass times specific heat capacity times the final temperature minus the initial temperature. So we know the initial temperature of the water, so this is 48, right? We do not know the final temperature of the water, so we will say that this is TF minus 48. They give us the specific heat capacity at 4200 joules per kilogram per Kelvin, and the mass of the water they give us as 3.2 kilograms. So you can solve for Q. And they also give us Q. Okay, so in this case Q is 9800. All right. Now the main thing to note over here is that the heat is being removed. So if 9800 joules is being removed, this should be negative 9800. So this is showing that energy is being removed from the system. Okay, so that's why you should put negative 9800. And so now when they solve for it, in this case we can just solve for this over here. So what we can do is that we can multiply both sides by -1 to get rid of the negative sign. So this just states that 9800 is 3.2 times 4200 times 48 minus TF. Okay, and that's because when you multiply -1 on this bracket, it reverses, right? So now, so this is 3.2 times 4200, and you're doing 9800, so you're dividing it by that. So therefore, we get that 48 minus the final temperature must be equal to 0.729, which means that the final temperature is equal to 48 minus 0.729, which is going to be 47.2 degrees Celsius. Okay? Now, the main thing to note is you might be thinking that, specific heat capacity, we were using, it has a unit of Kelvin, and the temperature is in degrees Celsius, right? So the main idea for that is that in this case, because the temperature scale, because the Celsius scale and Kelvin scale, because they're linear, then if the temperature rises by 10 degrees Celsius, this means that the temperature rises by 10 degree Kelvin. Okay, so they're linear scales. So in this case, even though the change in temperature was 0.729 Kelvin, you can just subtract it in terms of degrees Celsius, which is what we did. Okay. Now, if you want to be safe, then you can just use Kelvin for all temperatures, which is also a good way, right? So you could convert 48 degrees Celsius into Kelvin and do it that way. Okay, that can also work over here. So for example, if we do it that way, then we see that 9800 is 3.2 times 4200, and then this would just be this would be 48 plus 273 minus the final temperature. So this is just the Kelvin conversion, right? And then, so if you solve for it, you would just get the final temperature in Kelvin, and then you can just convert it to degrees Celsius. Okay? So that is for 3.2. It was a straightforward example. You just needed to apply that Q is mc delta T. Okay? Now, before we move forward, the main things you need to know for these problems is you need to know that Q is mc delta T. You need to know that the heat exchange, right? Heat exchange only takes place. So heat exchange will only take place until the final and initial temperature. So heat exchange will only take place until the temperature of both objects in contact is the same. So temperature of both objects in contact is the same. Okay? So that's an important thing. And then the other thing that we learned in the last video is that in this case, the energy gain plus the energy loss should be 0. Okay? So energy gain plus energy loss must be 0. This is the conservation of energy. Right? So if one body is gaining energy, then the other body must be losing energy, and then if you add them up together, you must get 0. So if you're gaining energy, it's positive, and then if you're losing energy, we use a negative sign for that. Okay? Okay, so now we can look at 3.3. So a mass of 200 grams of iron has a temperature of 300 degrees Celsius. It's dropped into 1 kilogram of water of temperature 20 degrees Celsius. Predict the final equilibrium temperature of the water. So as you know, the iron has a higher temperature and the water has a lower temperature. So therefore the iron is going to lose heat, right? And water is going to gain heat. Okay? And you can think of it this way. Let's say if you have an extreme case, right? Let's say if you have an entire ocean over here, okay? So if you have an entire ocean over here, obviously an entire ocean has more energy than, let's say, obviously the ocean has more overall thermal energy than, let's say, a drop of water, right? A drop of water at, let's say, 10,000, let's say a drop of water at, okay, so let's say the average temperature of the ocean is 10 degrees Celsius. And let's say you have a drop of water or actually we can make it better. So let's say that this is a drop of this is a piece of metal, so a small piece of metal, and let's say it's at 1400 degrees Celsius. Okay, so even though the temperature of the metal is higher, the overall energy in the entire ocean will be higher than a small piece of metal, right? That's going to be the case. But when you drop the metal into the water, it's not the ocean that will lose energy. It is the metal. The metal is going to lose energy. Okay? The reason the metal will lose energy is because it has a higher temperature. Right? So because it has a higher temperature, we have learned that it has a higher average kinetic energy. Okay? So the heat exchange will always go from objects that have a higher temperature to objects that have a lower temperature. Okay? So the overall energy does not matter, the temperature matters. So once again, let's say if you add up all the oceans in the entire world, and let's say their temperature is 10 degrees Celsius, and you just drop one small piece of metal, it's going to be the metal that is going to lose the energy and not the ocean. Okay? So so heat exchange depends on the temperature, and it will take place as long as you have a disproportionate amount of temperature difference between the two objects. So the piece of iron has a higher temperature, the piece of water has a lower temperature. So in this case, the main thing you will use is Q gain plus Q loss is 0. So this is a very important formula, Q gain plus Q loss is 0. So in this case, the water is going to gain the energy. So the mass of the water times the specific heat capacity of water times the temperature of the change of the water plus the mass of iron times specific heat capacity of iron times the change in temperature of iron is 0. Okay? Now we know the mass of the water is 1 kilogram. We know the specific heat capacity of water is 4200 joules per kilogram per Kelvin. Okay? And we don't know the change in temperature of the water, right? But what we can say is that in this case, we know, so the change in temperature of water, delta TW, is the final temperature of water minus the initial temperature. So we don't know the final temperature of water, but we do know that the initial temperature was 20. So this would be TF minus 20. Okay? Then after this, you're going to add it to the mass of iron. So the trick over here is that this is 200 grams. So you need to convert it into SI units. So this must be 0.2 kilograms. So this is going to be 0.2 kilograms times the specific heat capacity of iron, which we know is 450 joules per kilogram per Kelvin. And the change in temperature of the iron, so we know delta TI, so delta TI, we know that this is the final temperature minus the initial temperature. We don't know the final temperature, but we know that the initial temperature of the iron was 300 degrees Celsius. Okay? And now here's a very important thing. Like we have said, heat exchange will keep happening until both objects hit the same temperature. So that's why the final temperature of the water and the final temperature of the iron is going to be exactly the same. So that's why instead of this being a 2-variable equation, this is only 1 variable, which is that we don't know the final temperature. So this is TF minus 300, and we do know that the final temperature of both the water and the iron is going to be the same. Okay? And so after all of this, we get this major equation, and yeah, that's it. Now you just have to solve for TF, which is a simple math. Okay? The main part was creating this equation, and that's the main thing in physics, right? If you have to solve the equations, they're not as hard as compared to mathematics, but the main part is understanding the problem and formulating the creating the equation. That's the hard part. Okay, so now let's just we can simply just solve for this. Okay, so in this case, what we get is that 4200 TF minus 4200 times 20, which is minus 84,000, right? Plus 0.2 times 450, which is going to be 90, times TF minus 300 is equal to 0. So you get that 4200 TF minus 84,000 plus 90 TF minus 270,000 is equal to 0. Or sorry, minus 20,000 or 27,000. Okay. So if we put all this, then 4200 plus 90, so you get that 4290 final TF is equal to 27,000 plus 84,000. So if we add that up, then this comes up to be 111,000. And so the final temperature, if you do the math, then the final temperature comes out to be 25.87 degrees Celsius, which in this case is 26 degrees Celsius. Okay? So for these type of problems, you need to know this equation, which is fundamental. And this comes from the law of conservation of energy. Okay? So the net change in energy is always 0. That's what you need to remember. It's the law of conservation of energy. Okay? Now we can look at another problem from behind the book, right? So in this case, if you look at this given problem over here, you have a calorimeter of mass 90 grams, and it has you have a specific heat capacity of 420 joules per kilogram per Kelvin. Joules per kilogram Kelvin. It contains 310 grams of a liquid at 15 degrees Celsius, and you have an electric heater rated at 20 watts, which heats the liquid to 19 degrees Celsius in 3 minutes. Assuming there is no energy losses in the surroundings, estimate the specific heat capacity of the liquid. Okay, so for this one, the way you can do it is you need to draw a diagram. Okay, so you need to always visualize the problem. So let's just see what a calorimeter is. So in this case, a calorimeter, it is it's used for measuring the heat of chemical reactions. So we can think of it as a cup. Okay, so I don't think you need to know the specifics of this. That is more chemistry related as to what a calorimeter is. So we know that this calorimeter has a mass of 90 grams. So we're going to convert this to kilograms. Okay, so this is 90 divided by 1,000, which is 0.09 kilograms. Okay, so you've got a calorimeter of mass 0.09 kilograms, and it has a specific heat capacity of 420 joules per kilogram Kelvin. That's for a calorimeter. And now in this case, we can see that it's containing a liquid, so 310 grams of a liquid. So we can say 310 grams is 0.31 kilograms of a liquid. Okay, and the temperature of this liquid is 15 degrees Celsius. All right, now after this, you've got this sort of heat source. So you can think of this coming from a electric heater. Okay, so this is the electric heater. Now for an electric heater, it's rated at 20 watts, and in this case it provides heat to the liquid for 3 minutes. Okay, now in this case you just need to know that power is work done by time taken, and therefore if you multiply power times time, you get the work done, or the energy, which in this case is the heat energy Q. Okay, so you've got 20 watts, which is supplying for 3 minutes. So you should convert this into seconds. This is 180 seconds, or SI units. And so if you do this, the overall energy input is 3,600 joules. Okay? So you're providing 3,600 joules of energy to the system. Now, so what ends up happening, right, is that in this case, when you're providing that, then okay, so let's see how to go about it. Okay, so the main idea over here is that if you look at this calorimeter cup, and if you look at the liquid, then you have 0.09 kilograms of the calorimeter plus you have 0.31 kilograms of the liquid. So in total, this comes out to be, so in total this would come out to be 0.4 kilograms, right? So you've got both the calorimeter and you've got the liquid as well, okay? Now what's happening is that to this entire system, you're applying 3600 joules of energy, okay? So therefore, so just think of them in separate terms, right? You've got a calorimeter over here, and then you've got liquid, okay? And then you've got a heater, right? So what the heater is doing is that it's providing, in this case, the heater is providing 3600 joules of energy to both the calorimeter and the water, okay? So we know that initially the water is at 15 degrees Celsius. The calorimeter is also, so in this case, we can also say that and then, right, so now we can also say that the calorimeter would also be at 15 degrees Celsius, okay? So we'll say both of them are at 15 degrees Celsius because they're both connected. And we know that the final temperature of the water is 19 degrees Celsius, and that's the same thing for the calorimeter, okay? And they give us the specific heat capacity of the calorimeter, which is 420 joules per kilogram Kelvin, but we don't know this for water, okay? So in this case, the way we can think about this is that the overall energy supplied, so this is the energy supplied by the heater, right? Okay, so this energy that's supplied by the heater, some of that energy would go to the calorimeter, so we'll call this QC, calorimeter, and some of that energy will go to the water. So this Q is breaking up into QC and QW, okay? Now what is the energy in the calorimeter? Well, that's just the mass of the calorimeter times the specific heat capacity of the calorimeter, so that's Cc, times the change in temperature, which is final temperature minus the initial temperature, plus the mass of the water, the specific heat capacity of the water, multiplied by the final temperature of the water minus the initial temperature of the water. And this is equal to Q energy supplied, okay? And the main thing to note over here is that the change in temperatures for both of them will be the same because the calorimeter and the water are connected with each other, okay? So because of that, we can just substitute the values. So we know that the energy supplied by the heater was 3600 joules. We know that the mass of the calorimeter is 0.09 kilograms, specific heat capacity was 420, and the change in temperature was 19 minus 15. Okay, so the temperature went up by 4, and then the mass of the water, we ended up getting the mass of the water to be 0.31 kilograms. The specific heat capacity of the water we don't know, so we call it as C, and the change in temperature is once again 19 minus 15. Okay, so we solve all of this together to get the value of C, right? So if we solve for this, so 0.09 times 420 times 4, so 3600 is equal to 151.2 plus, in this case, 0.31 times 4, which is 1.24 times C, okay? Also, yes, I think for this question, I just said this blue liquid to be water. So in this case, this is just an unknown liquid, okay? You don't know what the liquid is. This would be unknown, all right? So I guess I saw blue and said it to be water, but in this case, this is unknown. So you can say this is the mass of the liquid and the specific heat capacity of the liquid that we would be looking for, right? So in this case, even though I said water, fundamentally the question does not change the same. It's still the same thing, right? It's just that there was some other liquid, but other than that, it's exactly the same. So if we solve for all of this, so I think this came out to be 1.24. If we solve for all of this, then this is 3600 minus 151.2 divided by 1.24, or actually, let's see, divided by, yeah, so actually this would be 1.21, not 1.24. So when you solve for all of this and you do the division, you get that C is equal to 2850 roughly, and the unit of specific heat capacity is joules per kilogram per Kelvin. Okay? And yeah, once again, the specific heat capacity deals with the Kelvin, and we ended up using the temperature values over here. But since we know that because the Kelvin and temperature are going to be linear scales, then if the temperature rises by 10 Kelvin, then it will also rise by 10 degrees Celsius. Okay? So, if you want to be safe, sometimes they do give questions where you need to only use Kelvin, right? So if you want to be safe, you can convert it and go through that. Okay? All right, and before we go, I think that's the main thing. You just need to know these pointers, that Q is MC delta T. The energy exchange only takes place until temperature of both objects is the same, right? Q gain plus Q loss is 0, conservation of energy. And then in the last question, we saw how the applied energy can be distributed between two objects. So, the energy of the heater ended up getting distributed to the calorimeter and then to the unknown liquid. Okay? And also one more thing. This video, I'll just put the name over here, Deep Think Mathematics. All right. So Deep Think Math actually. Okay. All right then. So see you in the next video. And we'll start off by doing phase changes. Okay, good luck.